All right. Yeah, so thanks for the wonderful introduction. And I'm going to cover a couple of different projects today where we are applying methods that I call the tech toolkit for social impact. And my lab basically has the aim that we partner with social sector organizations to try to make them more effective, and bringing together all the things that I have seen large technology companies apply, which include methods for heterogeneous treatment effect. That's where I got the idea, but also lots of other issues like how do you design and plan A/B tests and maybe advanced or more complex A/B tests, and how do you use the data from those experiments to plan future innovation. So I'll talk about a couple of our partnerships today, but we have a wide range. So what do I mean by the tech toolkit, first of all? Well, a lot of folks, I'm a founding director of our Institute for Human-Centered Artificial Intelligence at Stanford, and I give a lot of talks about AI. And a lot of times people feel that AI, the algorithm itself, is really the hard part of getting something done. But in my experience, where I spent several years working at the search engine at Microsoft, and I've advised a lot of for-profit large tech companies as well, the algorithm is just a piece of the overall pipeline. And there's really more of a cycle that you go through where you start out with some kind of observational data about outcomes, data from previous experiments, and you use that data to figure out what's going on. And there you might use methods, including types of methods I've developed in our lab, things like heterogeneous treatment effects. Who does the treatment work for? Evaluating counterfactual policies. What if we did something different in the future? What if we only gave the treatment to some people and not others? And what do we do with data if it was adaptively collected? What if bandits or other types of adaptive algorithms where they looked at the data and then changed what they were doing were used in the past? Then you figure out what you want to do next, prioritize in this kind of data-driven way. Could be recommendation systems, something like that. You do some kind of pilot experiment. Then you often do a larger scale experiment that can be used for decision making, but that also has a lot of steps. You have to decide what outcomes you're going to measure and validate them in some way. Do the pre-analysis planning, which can be quite complex if you're planning after the experiment to, estimate targeted treatment assignment policies. How do you know if you have enough data for that? And what if you're planning to do an adaptive experiment of some sort? Then the planning is more complex. Then after the experiment, you try to get generalizable insights as well as tactical insights, optimization, and make plans and kind of start the whole cycle over again. And so that kind of incremental innovation pipeline is really how things like YouTube and TikTok and search engines and Amazon all get good. They often start with a very simple product and then make it better over time, especially as they gather more data. And along the way, they also speed up the process by kind of automating and systematizing these steps. But at the beginning, it's often hard and slow. And that's one reason our lab works with these small ed tech companies and things like that, because they don't have the manpower to do that. And one of the things I like at the university is that with this type of pipeline, I can involve students of all sorts. So actually social scientists and economists and behavioral scientists are often better at some of these steps than people trained in computer science and machine learning, because a lot of this is about asking questions. It's figuring out what to measure rather than building a complex algorithm. So our lab is very interdisciplinary. Today, I'm going to talk about applications. And when we think about how these applications matter and why we're tackling them, well, I feel like there's a really important opportunity today to go from just impact measurement to impact creation. So we've had a lot of social scientists have gone out and tried to use things like randomized controlled trials or A/B testing to see what works. We can look at the effect of class size or bed nets. But in digital services, you actually have to embed yourself in the process if you really want to be influential, because the product is changing all the time. And you can't do a 2-year evaluation of a static product. Instead, it's changing every week. And if you want to measure it and you want to change it, you really have to be part of the technology development. And there's this moment of great impact we have, impact potential. We are digitizing services, and digital services can scale, they can be personalized, and they can be targeted. That's a really huge opportunity. It's also the case that sitting in universities, we can actually build them. With a few people working for a year, you can build something, and you can build something that could scale potentially to millions of people. So that's also a really exciting opportunity. So in my lab, I know we have some people who do methodology today. I'm not going to talk about methods too much. I just want to sort of advertise that we're working on a lot of the methods that are complementary to the pipeline that I just talked about. Everything from heterogeneous treatment effect to things about adaptive experiments. How do you test hypotheses after bandit data collection? We're looking at contextual bandits that learn targeted treatment assignment policy, and we have methods and theory papers about that. But today I'm going to focus mostly on applications. Aimed more at the applied community, our lab has been starting to develop more and more tools, as well as training materials. So for example, and these we share with our partners as well as academics. So for example, my machine learning course with Stefan Wager is available as a YouTube playlist. We have an older course that is a little bit longer that we have. We have tutorials in R that are in a book down format that you can download and run as well as read like a book. We have a lot of planning documents. We have a Shiny app for teaching about bandits where you can simulate different bandits. And then we have a lot of open source software, GRF being the most popular, but a variety of others as well. But today I want to talk about how all these things are applied, although creating these tools and open sourcing them is sort of part of our impact, because these tools we have demonstration projects around the social impact applications. So let me start with first something where we're using offline data to estimate targeted treatment assignment policies. So, and what do I mean by a targeted treatment assignment policy? That's like when I target a treatment to different people. So here's an example of a sort of a decision tree format for a targeted treatment assignment policy. And this is taken from an experiment that I ran that was partly designed to illustrate techniques for contextual bandits. So in this, we were gathering data from people on a survey platform. We were asking about their political views, and then we asked them which charities they would donate to. And we wanted to try to understand whether we could, in a sample size of a couple thousand people, learn how to target which charity we gave to people. The targeting is kind of extreme here, but we see that people who have, say, a view that's, what they think that you should be able to bear arms, and you don't care about global warming, then asking people about donating to the National Rifle Association is most effective. But if they like global warming, we might actually target them, ask them about the charity Planned Parenthood. So to learn that type of policy, you can learn it online by running a bandit, which is what we did to get that policy, but we can also use historical data from randomized experiments. So in this case, we used a purely randomized experiment to gather data. And we're going to, actually, somebody asked in the chat about Contextual Bandit. Let me come back to that, and I'm going to define it in an example in a few minutes. So in this paper, we're looking at a randomized experiment that was run to try to give people text messages to prompt them to fill out financial aid forms. And in the United States, the financial aid forms are very complex, and a lot of people don't fill them out and thus don't get the financial aid that they're eligible for. We had 25,000 students in one year and 40,000 students in another year. They had different colleges, and so the environments weren't exactly the same. And what we found in this evaluation is that nudging people with text messages to apply for financial aid increased their on-time submission by about 6 percentage points in 2017 and 12 in 2018, which was large as a percentage of the baseline, going from 37 to 43% in 2017, for example. This is what the text messages look like. You got this series of text messages that reminded you and gave you the links to go and fill out the forms. So in this case, what we want to do next is to figure out, well, are there some people for whom this works better than others? If we know for whom it works, we can give it to them, and then we might develop other treatments for people where it doesn't work. In addition, although the sending text messages is cheap, we might also want to think about prioritizing some kind of human intervention as well. So we want to think about estimating a treatment assignment policy. We want to see if personalization is worthwhile. So the data-driven approach to heterogeneity, we start by estimating conditional average treatment effects, which we do with our GRF package. We then can evaluate that heterogeneity. We can compare the different group characteristics, and then finally estimate an optimal policy. And we do that either using non-parametric methods, just give the policy to who it works for best, or we can also use parametric policies like this type of decision tree, where we have a method called policy tree that you can get to also from the GRF package that estimates decision trees. So when we estimate the heterogeneous treatment effects, we then put the observations into groups, and in this case, we do them according to the estimated quartile of treatment effects. So in this case, higher quartiles of treatment effects should have higher ATE, average treatment effect estimates, and lower quartiles should have lower average treatment effect estimates. And this is done using held out data. We use cross-fitting, so that the data that's used to put you into a quartile isn't the same as the data that's used to compute the average treatment effects. And so the dots and the error bars in these pictures are basically just simple average treatment effects within a group. So we're using an algorithm trained on one part of the data to assign you to a quartile. And then in different data, we're computing the sample average treatment effect. And so this is essentially assessing the quality of our heterogeneous treatment effect estimation. So in an ideal world, these are upward sloping, and higher quartiles are uniformly getting higher treatment effects in test sets. And they're not here. There's some differentiation, but we see that it's kind of noisy. And in fact, we see a little bit of a downward slope in the fourth quartile. And this is a pretty common way that these pictures look. If you have kind of noisy data, your signal to noise ratio is not that favorable. And so if you try to go estimate treatment effect heterogeneity as a function of covariates, due to sampling variation, you're going to find something, but whether or not it really holds up in a second data set depends on how much heterogeneity there is in practice. So here we see some separation, but not all. And when we go and look at the covariates that underlie this, which covariates put you in the higher quartiles, the biggest difference across groups is enrollment status, whether the person had actually dropped out of college at the time the text messages were sent. Now, this is a college that serves first generation people that are adults that are often working full time. So people drop out and re-enroll all the time. So just being unenrolled doesn't necessarily mean that you're not interested in financial aid, but we're finding that the people who weren't enrolled are the ones who had the biggest, who were enrolled were the ones who had the biggest effects. Next, and I should mention that since we wrote this paper, we've released a new way to evaluate treatment effect heterogeneity called RATE that Stefan worked on, and that's now part of the GRF package. And that actually allows you to assess treatment effect heterogeneity with something like an ROC curve from classification models. And so you should check that out if you're interested. So then we want to go estimate a treatment assignment policy. So we're trying to now estimate a policy that maps from covariates to treatments. And then we want to estimate the impact of different alternative policies. So to think about it, that might seem like a complicated problem where the policy is a potentially complex function mapping from the space of X's to the space of treatments. But actually, if you have randomized data, evaluating a policy is not that hard. So over on the far left, I've got the axes are representing covariates, say X1 and X2. These are different covariates. And then the points are representing observations, and the shapes are showing whether in the data that you have, the historical data, they were assigned to control, that's the circles, or to treatment, that's the squares. Now I can think about how can I evaluate a counterfactual policy? Well, let's consider a counterfactual policy that paints the some of them red. So you see this shape in the middle, that's a complex policy that doesn't have monotonicity. So we're going to say, what would happen if I, instead of just randomly assigning the treatment, I assigned the red people to the treatment and the green people to control? Well, if originally my data was randomly assigned, then in each of these regions, I'll also have a random assignment from treatment and control. And even though the policy itself might have a complex shape, evaluating it just means first divide my data into two groups, red group and green group. And then I can just take the sample average treatment effect within the red group. That's the benefit to treatment for the red group. And if that's positive, then treating the red group is beneficial. And we also hope that the treatment effect in the red group will be bigger than the treatment effect in the green group, because we're choosing to assign to the red group and not to the green group. And again, we can make non-parametric policies based on non-parametric estimators of treatment effects, or we can use simpler partitions, and that in the covariate space will look like rectangles getting assigned to treatment or control. And in different projects, we use different, you can think of the tree policy as a form of regularization, and in some cases that performs better. It's also more interpretable. So basically, that's what we go and do. We do a non-parametric method. We build a forest based on estimated treatment effects. It does have some overfitting problems, but it also allows more flexibility. And then we go and evaluate those things by taking sample average treatment effects. So we then compare the performance of multiple different targeting algorithms. So in this picture on the x-axis, we have the percent treated going from 0 to 1. And the red line shows how average outcomes change as you increase the percent treated. And if you're doing random assignment, which is the pink line, then as you treat more people, you just give the average treatment effect to more and more people. So on the far right is the average outcome if everyone is treated. On the far left is the average outcome if no one is treated. And if I randomly assign people, then my expected outcome gets bigger and bigger at a constant slope as I increase the percent treatment. Now in this picture, we show the alternative expected benefits if we use a bunch of alternative different treatment assignment policies. And so if we particularly target according to our estimated treatment effects, that's the CATE, that's the olive line. And it actually doesn't do much better than random assignment as we start treating people. And only later does it actually come up above random assignment of people to treatment. And that makes sense if we go back to these pictures. We really weren't able to differentiate very well among the low treatment effect people. Our model just can't tell them apart, but we can tell a bit around the middle of the distribution whether who's the right people to treat. And you see that by showing that the average outcome is better when I do targeted treatment assignment policies. But actually something does even better than our estimate. And you can think of that as a targeting based on just a single goal. And that is based on the probability that people would, the estimated prior probability that people would fill out the form to start with. And so basically what we're finding here is that targeting people that were already likely to do the activity for a nudge is most effective. It can also be effective to target people based on enrollment, and enrollment is actually the highest predictor of whether they will fill out next year. The worst possible thing is to target people who weren't likely to fill it out. And so one of the points here is that a priori, you don't know whether you should be targeting people who weren't going to do the thing or who were going to do the thing. And in this case, it really matters. So this type of analysis can help you determine treatment assignment policies. Now, ideally, you would like it that if you targeted by estimated treatment effects, that would give you the highest curve. But in this case, it's kind of noisy. And so, yeah, it's, you know, somebody's pointing out in the chat, yes, there's a little bump up at the bottom, but it's not that statistically significant. So, but in the end, this is a data-driven exercise. So this is how we've been doing it for a long time, these pictures. And then Stefan recently wrote this paper that kind of put some formal statistics around this so that you can test like the area under the curve using something called the rate. Now let me move to my next application, which is recommendation systems. And here, a recommendation system is basically to try to, we're going to use historical data on users' interactions with a large set of items, and then we're going to predict how they're going to engage with items they haven't interacted with before. So a lot of times people think about recommendation systems as being very different than treatment effect estimation, but one way to think about it is it's just an extension of the previous type of experiment, except when instead of having a treatment and control, now I have thousands of treatments. But I can still do the same kind of exercise where I estimate targeted treatment assignment policies. In this case, though, it's going to be harder to do off-policy evaluation because we're going to have a problem with overlap. Like if there's thousands of treatments, then lots of people aren't going to see most of the treatments. And so running a randomized experiment live is often much more important in this context. So this is an educational application from India. And this application kind of shows people stories to read, and it helps low-income families in particular, where they might not have a lot of books to read, and also the parents might not be that good at reading English themselves. This is a look of the flow. There are different types of consumers, B2B, B2C, and this is showing how people flow from the different places into viewing a story, and then some people don't start the story. Those would be the, like, say, the yellow below. And then some of the people who start the story, not everybody completes. And the red people are people who go all the way through to the end. And so the idea is to try to recommend stories so that people will go through this flow more often. And in collaboration with the app, we put a utility on this. So we give, if we want to judge the quality of a recommendation, we'll give it points if the user views it. We'll give it more points if it's the user starts the story, and then the most points if they complete the story. But coming up with how you even evaluate success can be a challenge of itself. Then using historical data, we estimate a model to try to estimate for each user, what would their utility be on a story. And so we use a latent factor model as our leading model, and this is basically referred to as collaborative filtering in the machine learning literature. But it's basically just a latent factor model where we're estimating latent factors for each story and latent preferences for each user, and then making predictions based on that. We can also consider simpler models where we just use two-way fixed effects, and that is, we have a fixed effect for the user. Some users read more than others, and a fixed effect for the story. And you can think about targeting that way as just targeting based on popularity, how much people like the story. Just use it, and if we target in that way, we'll basically give the same stories to everybody. Stories that look popular will be given to everyone. So in offline evaluation, we found that the mean squared error was the lowest in this PYTF, was our abbreviation for the collaborative filtering model that we used. And it also beat using a model that the mean model basically looks for popularity, but it doesn't factor in that some users are more active than others. And so it actually gets a little bit of a different selection of who's popular. Then we also look at different links of history for users and stories. And we see that people who stories that don't have a lot of interactions, or users that don't have a lot of interactions, had higher mean squared error than users and stories that had more interactions in our offline analysis. So using that, we ended up choosing to implement the algorithm only on users and stories that had sufficient history. We then went out and ran a randomized experiment. We did.
Sorry to interrupt you. We have some questions in the chat here. Maybe Devdat, if you ask yours, and then Coach Hero quickly. Devdat?
Hi, I was just wondering, Susan, when you do your collaborative fitting model and you get the latent variable, I mean, are those interpretable, or they're just something that pops out from just factorizing the matrix?
Yeah, so we didn't find them. One of the problems here is we seem to not have very good features about the stories, which is one reason this is important. So they're called animals or sports, but that didn't really line up very well with the factors. So in this particular case, we're not finding them interpretable. One of the things we're working on in other projects is estimating the student proficiency and seeing how that evolves over time. And then in some other apps we work with, there's a natural progression, like some stuff is harder than others. So in those applications, we're going to push harder on the interpretability. We would like it to be interpretable. We just didn't find much interesting to show here, unfortunately. But that actually is something we could do more with, like we could look at the text. We just haven't done that yet.
Thanks, Susan. We have another one, but we can take it at the end from Coach Hero.
Okay. So here we ran this randomized experiment where we gave some people the recommendation system, and then that's actually competing against the human curated system that they had in place before. And so I should say that you might think that like the recommendation systems are everywhere. So this type of study must have been done a million times. We must have lots and lots of studies that compare having a recommendation system to not having a recommendation system. But that's actually not true. There aren't that many illustrations. And that's partly because, like, how are you going to convince TikTok to like turn off their recommendation system? You know, that's not something you would normally do in practice. And then even if you did, it would often be proprietary, a measure of how good your recommendation systems are. So there aren't that many applications where people have really assessed them live on live users. And then in the EdTech context, there aren't that many EdTech companies that actually have recommendation systems, like very, very few. And a lot of them are small, and there's privacy issues with the data. So there just haven't been evaluations like this done before. And one reason we're able to do it, and of course it takes engineering to turn something off, right? So here, because we built the recommendation system and we were implementing it for the first time, this was kind of a unique opportunity to turn it on and see what the benefit was of turning it on. So here in the top, we kind of see what this looks like non-parametrically. We see this cumulative distributions of the treated and the control group. And we see that the treatment group the distribution is shifted to the right, and it looks, you know, basically through the most of the mileage is coming in the middle and low parts of the utility distribution. We then can look at average treatment effects as the potential of baseline, and we look at it in two ways. We tested it just on one part of the app, not called the recommended stories path, although previously it was manually recommended stories. Now it's machine recommended stories. And then we also looked at what happened on the overall app, because you might imagine that having a really good recommendation system in one part of the app would just steal engagement from other parts of the app, and there might not be a net increase. So we see, as expected, within the recommended stories path, really large increases in engagement. So 61% over baseline, 76% over baseline, 82% over baseline. So very large statistically significant effects. And then we see positive, but only marginally statistically significant effects across all paths in terms of increase. So there is some, we're not cannibalizing the other paths. There is some positive spillover effect to other paths too. And overall, you're spending more time on the app. But a lot of that is concentrated in the part where we improve the recommendation system. We then looked into who was impacted. We looked at what we called niche users, who were users that were reading less popular stories, as well as high utility users. And we find that the average treatment effect is highest for high utility and niche users. And so that's where we find the biggest effect. In the bottom, we break things out by the story's prior popularity, and we find that the impact is largest for these rare stories. So the control was also showing rare stories sometimes, the human curated, but the algorithm is much better at targeting rare stories to people who would actually like them although there's effects all up and down the distribution. And then finally, we do off-policy evaluation. We didn't actually test live a pure popularity-based model. We just compared the editorial to collaborative. Now, there's a problem, well-known problem, that now we didn't actually run the popularity-based algorithm. So this is the problem of off-policy evaluation. And more popular stories are not uniformly shown, but less common users read a higher share of popular stories. So we use a variety of off-policy evaluation methods. Here, the simplest one to understand, we're just running a regression where we control for the user's past utility and their past utility in consuming different types of stories. And that's a way to adjust for the fact that different users are seeing different types of stories. And in this regression-based approach, we see that the collaborative is better than popularity. But when we have a richer model, that gap closes a little bit. So the distance is close across a couple of different ways of adjusting for this unobserved heterogeneity or unobserved confounders, a couple ways of adjusting for those. We see similar results across those. So it looks like there's a benefit to the AI algorithm over just pure popularity, but it's not a really big difference. So that's something we might want to test again in the future.
Susan, one question with the online and offline policy tests here. So how do you make sure that the samples are aligned? So the sample from the online might be different from the offline because you did it during 2 weeks, and maybe the characteristics of those differ from the actual sort of offline. So how do you align those two samples?
So it's a big problem. And actually, I have another project that I didn't show you today where we were targeting agricultural calls to people in India. And so we ran a randomized controlled trial for 3 weeks, gathering data. And then we estimated a policy, and we estimated in a held out test set of our training data that we would get like a 10% improvement in engagement, but then we only got like a 2 or 3% improvement. And it turned out that like there was, in the week that we tested it, there must have been like a holiday on Sunday, which was we found in our training data was a great time to call, but then nobody picked up in that time.
Right, that was actually what I thought.
In the real thing.
Yeah, like people being on vacation, or there's some event that you didn't, was possible to control for.
Yeah, so these are big problems, and especially if we get this one shot to, in the India case, like we had, we can't run another experiment now for reasons. So we were stuck with what we have, and we ran what we ran, and we got unlucky with a bad week. And so now instead of the paper showing, a 10% gain, the paper showing a 3% gain. Then we try to go back in the historical data and actually try to understand how much variability is there week to week, and sort of how much risk do you have if you target based on a short time period. So that's one reason in the tech world they kind of keep experimenting all the time, because then they can get a better sense of these holiday effects and stuff and try to adjust for them.
Right. Thank you.
Okay, so now let me briefly show you about the last experiment, and I'm going to skip some slides here from a longer talk, but here we collaborated with the World Bank to deploy a tablet application that helped guide women through choices about contraception. So this is an application now not where we're targeting individual users, but we're targeting service providers. And that's another great application of AI, is helping teachers be better teachers, or helping counselors be better counselors. And so that's what we're going to do here. And we're going to use an adaptive experiment. I promised I'd come back to that. So here we've got women in a hospital in Cameroon who are nurses who are counseling women about contraceptives. When we originally designed the study, we thought that a lot of the impact would be getting women to switch from short-acting contraceptives to long-acting contraceptives. And it turns out the failure rates, especially in developing countries, of short-acting contraceptives are very high, because people can't get back to the clinic, they run out of money, and so they stop using them, and the failure rate is therefore, there's a high rate of unintended pregnancies. But it turned out what we found, where I'm not going to talk as much about that, because it turned out what we found was that that a lot of women were just leaving the clinic without any contraception. And so just getting people to take any form of contraception was the more important margin. The hospital is in Cameroon. And what we do in this project is we deploy a tablet application that guides nurses through both how to structure the choice of contraceptives as well as how much to charge contraceptives. And so, but for reasons we couldn't actually test tablet application versus no tablet application. So because of the way that, for operational reasons, so all the nurses are going to use the tablet application. But for some of them, the tablet application is going to rank the choices and go through them in a ranked order. We call that shared decision making because the tablet is sharing in the decision. The control method, if you like, is where the women choose which ones they want to hear about after a brief overview. So the shared decision making is more input from the algorithm. And this algorithm is not a recommendation system type algorithm. It's one that is based on people's preferences and history. So it's going to rank things according to that. It's going to rank the methods according to their scientific characteristics and their health characteristics. What we're going to be learning about is how to target discounts. And also, in principle, if some women like being in the driver's seat and controlling the conversation, we would target that to different women. The TLDR is going to be that basically the ranked lists the shared decision making is going to be better for everyone. So we're not going to find that there's some, like say, highly educated women that do better by guiding the conversation more themselves. So the way that this ranking system works, we can see how often it ranks different things in different positions. It most frequently ranks IUD and implant in the top positions, but it also sometimes ranks injectables and pills, especially pill can be in the top position, and injectable is sometimes in the is most often in the fourth position, based on failure rates and compliance. So we start out by running a purely randomized experiment. It's a factorial experiment where the prices range from $7 to free. So basically full price to 50%, 75% discounts, et cetera. And then we also randomize the kind of tablet ranked decisions versus the kind of women choose where to start treatment that we call IDM. And so there's some complications. Let me skip over those. We survey people afterwards to see whether they dislike either of the approaches and whether they feel pushed. And we find that there aren't really substantial differences in terms of respectful care or method selection across the two methods. So we don't think that the women feel like they're being pushed into things. We also find something interesting, which is in the blue is the shared decision making where the tablet ranks things. And we find that actually they discuss more methods when the tablet ranks things than when the woman chooses. So it's not like the nurse and the tablet are pushing people to only discuss one thing. In fact, when there's a ranked list, they tend to discuss more different methods. Here's the results from our original purely randomized controlled trial. Method in mind, MIM is a group of people who basically don't accept the counseling for various reasons, but they just get discounts. Let me focus on the bars on the right. We see among the IDM people, that's the one where the women choose the order to talk about things in, the discounts are extremely important in terms of getting adoption. So 28% leaving with a long-acting contraceptive versus 11% without the discounts. So the discounts are super important. We see the shared decision-making where the tablet ranks things has higher overall rates of adoption, but the discounts don't make much of a difference, although that's kind of noisy. So this original pure randomized controlled trial phase already shows us that it looks like the ranking is good, discounts matter, but discounts are not as important once the woman is sort of given the recommendation that says this application thinks that this is the best method for you given your risks and issues about side effects and things like that. Then we go to an adaptive part of the experiment, and that's where we get to the bandit. What we're going to do is try to adaptively learn how to target these different treatments. And in particular, we have a budget constraint. And as you know, in constrained optimization, we can optimize we end up optimizing a weighted average of different objectives. So here we are going to reflect the budget constraint by putting a multiplier on the cost. And then in terms of the failure rate, we're going to use failure rates from the different contraceptives from the medical literature, but we're going to prioritize failure for younger women more, so that our objective function cares more about, say, teenagers getting pregnant. Then we're going to, again, randomize. We're going to cut out one of the prices to simplify the experiment. And what we want to do is over time, put more weight into policies that are good. So at the end of the pilot phase with the pure RCT, we first look at what a good targeted treatment assignment would be just based on that data. And that already divides the women into 4 groups based on their age and whether they had a recent delivery. So based on the pilot data, we think that all the women should be getting the shared decision-making, all the different types. But the discounts, if we have a budget constraint, the discounts should be concentrated on women who just had a baby and are older, and young women, the youngest women under 24. And then we still have pretty noisy data, so we want to do 2 things. We want to go out and collect more data to learn if this really is the best way to assign the treatment. And then second, we also want to gather data about this policy, or the best policy, the policy we learned, so that if the government was going to go out and implement it, they would actually know how much it's going to cost and how much benefit there is, how worthwhile it is. So we then go out and run what's called a multi-arm bandit. And so in the first stage, we had this pure random assignment probability. So all the different arms would have different, similar treatment assignments. This is hypothetical. I'm just showing with 4 arms, but we have more in practice. But what a bandit does is, as we go along, the arms that are doing the best get more units assigned to them. This is going to help optimize the exploration trade-off. And it's also going to make the people in the experiment better off, because we're going to assign more people to the best performing treatment. By the end of the experiment, most of the people are getting assigned to the best treatment. We also end up with a very precise estimate. So if you look on the right, we would have a tight estimate of the value of the best treatment arm, while we would have noisier estimates of bad treatment arms. But we don't care, because we're not going to go implement them. We don't really need to know how good a bad treatment arm is. So this is a picture of what's going on behind the scenes. Here we're using Thompson sampling. At the beginning, you might have different uniform priors. You might think each arm, here we have 3 arms, each arm has sort of the same prior distribution. But as we collect data, we will collect more about winning arms. So in this picture, arm 2 is winning, and it has tighter posterior. We've gathered a lot of data about it, so we're confident that it's high. But there's still some probability that arm 3 is good. You can see that we haven't gathered as much data about arm 3. So there's still some chance arm 3 is better than arm 2 if we collected more data. And so the Thompson sampling heuristic is going to assign the treatment arm according to the probability that each arm is highest. So that's basically what we're going to do. We're going to do it here in a targeted way. So we're going to use different probabilities for different groups of women. And we're also going to do some things like put lower bounds on the assignment probabilities. The final thing is, because we want to test hypotheses at the end, we're going to have a pure evaluation phase at the end, where we focus in on the winning policy to make sure we have enough data about the winning policy that we can tell the policymakers about it afterwards. You can see here how the assignment probabilities change over time. And in each of these 4 groups, we see that it's really hasn't converged by the time we get to the evaluation phase. So it was important for us to have an evaluation phase where we really focused in on a winning policy. Otherwise, we would still be randomizing a lot. And we only have a few thousand patients overall across the entire experiment. So we're really still a little bit short on data. But we see by the end here that in the young group and in the old group who had a recent pregnancy, that we get free LARCs, so full discounts, And we get 50% off discounts coming in the other two regions. And that's what we evaluate at the end. Now, at the very end, so this is the policy we learn at the end after the adaptive data collection. And the main change from the pilot was that we got a bigger discount for one of the groups. Then in the final evaluation phase, we put 60% of the people into our estimated best treatment, 30% into a pure control group, and 0.1 otherwise, so we can test some alternative hypotheses. I'm running short on time, so let me just focus on the final results where we compared the learned targeted treatment assignment policy to the control. And overall, we got 40% of the women leaving with the targeted treatment assignment policy, while only 23% left with a long-acting contraceptive in the control. And the control was using the women choosing what order to go in, and it also didn't have discounts. Now, you might want to go back and say, well, I'd like to separate out what about the discounts versus what about the app? And we will do that, although we're not as well powered to do that, because remember, the last phase of this experiment, we were really focusing in on two alternatives, control versus a targeted policy. And you can see we have these very tight standard errors around the learned policy. So the benefit of this is that we really gathered a lot of data about the thing that we would recommend implementing, at the expense that we didn't gather enough data to test other hypotheses. Overall, adaptivity had these benefits. We got more data about good policies, better precision in estimating the value of the recommended policies, and it was better for the women in the experiment. But the cost or complexity, in addition, we would have high variance if we reuse the data to test other hypotheses. What we still haven't done yet is actually some of my research looks at statistical methods for using the adaptively collected data for hypothesis testing. So this is just using the evaluation phase, which was a pure RCT between two policies. We haven't actually pooled all the data for the whole experiment yet, which requires more advanced statistical techniques. Okay, let me stop here and happy to take questions. I'll leave this up because there may be questions on this, this last paper.
Thank you very much, Susan, for that amazing talk. There were some questions related to the Thompson sampling, so perhaps we can start with those. And I would like to invite Devdutt to start off. I will go into unmute you in a second, Devdutt. There we go.
Yeah, hi, thanks, Susan. So that was very interesting, but I was just wondering that if the goal here is to identify the best treatment, the best arm, then Thompson sampling is not the best algorithm to do that. I mean, Thompson sampling is great for regret, but not for best arm identification. Maybe there are versions of Thompson sampling, like the top two Thompson sampling, which are better for best arm identification.
That's right. And so actually we in other papers, we are focusing in on that. So there's also like exploration sampling, which basically slows down Thompson sampling by Casey and Sotman. So absolutely, it turns out, so here we really did have two goals, and that was actually part of what we did in our pre-analysis planning here, is we were trying to balance learning with the outcomes for the women in the experiment. And so given that we really hadn't converged very much, the different algorithms wouldn't be that different here, in that the differences really kick in as you start to narrow things down, and then you avoid, you stop leaning into the very best arms. So for simplicity, we ended up focusing on Thompson sampling, but it actually didn't matter that much. But that's a great point. And actually, for social scientists, we're often more interested in learning than we are regret during the experiment. And the computer science literature has focused much more on the outcomes in the experiment than they have on learning afterwards. So that area of further refining algorithms for learning, or to balance learning and regret, is something that our lab is working on now, but exactly because of applications like this. So here we just did simulation studies to sort of compare the different things, different algorithms, and we saw it didn't matter that much in our small sample size. But in general, you would like the algorithm to be able to accept multiple objectives and to balance them.
Thank you, Susan. Next up is Alexander Gower.
Hi, Susan. Thank you so much for your talk. This is really, really cool work. I have a question which is kind of based on my experience helping policymakers in public life, and it relates to understanding of these figures, because obviously these techniques are they are to some degree interpretable, but they require some statistical knowledge to interpret. So specifically here with the fact that you don't collect more data on the policies which you deem not as effective, is that something that you run into problems with people not saying, okay, well, why did you stop looking at these?
Yeah, well, so I mean, this is in partnership with the World Bank, and this was a big, expensive project. And one of the reasons that we did it, and one of the reasons they partnered with us, was that they had not run this type of adaptive experiment before in this kind of context. So this is partly a demonstration project. And we partly justified it. I mean, part of the reason it was interesting to them was that it had these ethical benefits. So we would explain that rather than subject women to, a bad tablet application for a year, we were going to be, as soon as we were learning that this one tablet application was good, we would be giving it to those women. So that was viewed as a desirable objective, even if people don't really understand the details of how it works under the hood. Then the second thing, though, is that, we, despite wanting to demonstrate the benefits of bandits, we also wanted to get policymakers to implement the app, because this turns out this is like a really beneficial treatment, and it's inexpensive, and it actually has other applications too, like other types of help. So we really wanted the policymakers to be confident. So this data I'm showing here on this slide is from a pure randomized controlled trial. So it's kind of like, you can think of it as we're testing one configuration of the app, where the app customizes discounts and gives advice in a certain way against the control. So this is a pure randomized controlled trial, and they don't have to understand anything about how we got here, because at the very end, we're just testing A versus B, and everybody gets that, and we have nice confidence intervals. So that's one reason, it was kind of sad here to kind of cut off learning. If you see in round 4 of this, we're not completely sure what the best thing is, and we're not completely sure that we really need these bigger discounts. Say for group C, the pink and blue differ by the discount, and we had to cut it off and just go with the winning arm, even though it easily could have switched back later. So we're not sure we got the best thing, but we wanted to have a pure evaluation phase, so that, because if we didn't have that pure evaluation phase, we just wouldn't have that much data about the winning policy. And we certainly don't want to go tell the policymakers about a random policy. That's going to be really confusing. So we stopped the learning and gathered data in a pure RCT, and that's really aimed at the communicability of it. It's also good for statistics, though, and frankly, I wrote these papers about using adaptively collected data to test hypotheses, and we're still working on those methods. But frankly, in practice, if I ever cared about it, I would always have an evaluation phase where I stopped collecting data adaptively. And that's what our lab is always doing, because it's messy and it's noisy. Unless you have enough money to run the thing until things really converge, most things where you're paying subjects, or you're advertising for subjects, or you have a partner with a small app or something, you don't get to this phase. You never get there. Like you're not sure at the end. And in those real world settings, you really, it's hard to draw clean conclusions at the end with precision unless you have an evaluation phase. And by the way, that's more, I'm sorry, that's also more like what the tech companies do. Like the tech companies will do pilots and they'll do offline evaluation, but in the end of the day, most tech companies do want to see a pure A/B test, algorithm A versus algorithm B. They don't trust it if you do offline evaluation for big decisions. And so you can think of that as like there's an exploration and learning. They might do a tuning experiment, try lots of arms, but then whatever they come up with, they do test the final thing. They don't just draw inferences from a complicated, low-powered, multi-arm thing. They roll out the algorithm for a large group and let it run for a little bit and make sure that it actually works.
Thank you, Susan. Next up is William Hughes, and after that, Koji or Shiva, if we have some time there. William, please feel free.
Yes. So I just wanted to ask what I put in the chat message. So how well does this algorithm deal with conditions changing? For example, if there's a drought or some other macro level event, that means that the information you have about the people starts implying that different policies are optimal. So what I intuitively would fear is that the bad strategies that you have stopped doing suddenly become good, but you don't find that out fast enough. So yeah, my question is, how does this deal with that kind of setting?
Yeah, it's really doesn't, and that is a problem. I mean, it's a challenge, and trying to get a partner organization though to keep running experiments like this is really hard, because the partners we work with, they have like one data scientist, and they've got to, they're putting out fires all day long. They're seeing like, why did the system crash yesterday? And, are the lights on, basically? And so trying to monitor and maintain something like this is something that's very difficult for them to do. They have much higher priority engineering challenges that just involve scaling and building really core functionality. So, and then in this context in Cameroon, it's very administratively complex to be continuing to run an experiment and collect the data. So, you're kind of stuck with making a recommendation and going forward, even though these time varying things are a big problem. And as I mentioned, it kind of, it was very sad because we were working with this thing in India where a nonprofit had created the service, and then they were handing it over to the government, and there was an end date for when they were handing it over to the government. And so we were running the experiments right up to the last day. But, we had a data gathering phase, and we had an evaluation phase, and we got unlucky, and then we're handing over our recommendations to them, but we can't necessarily keep experimenting, and it may not be the best thing. So that's it's a real challenge when you're working in the world. And frankly, it's a good reason that a company might say, maybe we should just keep it simple, because you can make things worse. Like, suppose we think that you should call everybody on Sunday, but Sunday was just really good in our training weeks, and then it's really bad forever after. They might have been better off just giving the same thing to everybody. So these are real risks and concerns, and you just sort of mitigate them as best you can. In the real tech firms, they try to keep experimenting and keep testing, but frankly, they screw up too, as we all see. Sometimes they destroy democracy or other stuff, So by not really monitoring what's going on, or not monitoring all the secondary metrics, not really digging into why something is working. And I think that's partly where social scientists can be really helpful in the wild, because we're often the ones asking, well, why? Well, what about this? What about that? Why? What's underneath it? Is it stable? Is it counterproductive? And you need somebody to ask those questions and then take the time to dig in the data and figure it out. And that kind of curiosity-driven, interrogation of your data is often there's just not time for it in a world where your engineering team is getting rewarded for shipping one more thing, and they do a 1-week test, and then they're done, and then they move on. In that world, there's just, it just doesn't happen that people ask these questions necessarily. If something's really important, like seasonality or holidays, then they eventually build it into the system. But, there's lots of things that just never even get found.
Thank you, Susan. We have one more here in the chat, at least. Koichiro, please go ahead.
Thank you. Thank you for the very much, stimulating talk, Dr. Athey. My question is about heterogeneous treatment effect estimation. And I am epidemiologist by training. And in epidemiology, we often distinguish effect heterogeneity from what we call causal interaction. So for example, let's say we are interested in estimating the heterogeneous effects of certain medication. And let's say we find, heterogeneity where the treatment, the medication is more beneficial among non-smokers. So the implication of such heterogeneity would be to assign the medication to non-smokers to make it more effective. But if it's truly, what we call cause interaction, the implication of that would be, we can intervene in the patients and then promote smoking cessation to make the treatment, the medication more effective. So I'm wondering if you could share your thoughts on how we can or cannot use the existing methods to get insights on such causal interaction.
Yeah, so I obviously, so that's a great question. And I mean, in general, when I think about these machine learning methods coming together with traditional approaches to causal inference, the machine learning, it doesn't really solve fundamental identification problems. The machine learning is really about just operationalizing them better, more efficiently, dealing with, being honest about your data fishing, or helping you have a pre-specified algorithm that looks for heterogeneity more systematically, and so on. So, the challenges in determining whether, from your existing data, telling people to stop smoking would be more effective. All the same problems you had before remain if you use machine learning methods as opposed to more traditional estimation methods to do it. I would say that you do have to be cautious if the machine, if you just throw in a black box and it says, oh, here are the 6 dimensions of heterogeneity, you can't stop thinking about what those are if you're actually thinking about trying to target people causally. So you still have to use your domain knowledge and look at your assumptions and do supplementary analysis to try to assess whether you could take action based on those. And I do agree, some people are concerned that the machine learning methods kind of make people stop thinking. And I definitely don't advocate for that. I was, a structural, person who estimated data generating processes before I did machine learning. So I'm very attuned to the importance of thinking through your data generating process. And that should be a complement to machine learning, to me, not a substitute. In terms of what we actually have, our GRF package has what we call MGRF now, where you can look at multiple outcomes and multiple treatment arms and try to estimate multiple causes. And in particular, if you had a factorial design or something where some people got smoking cessation and some people got, the drug, and you want to look at combinations, the MGRF package can now address that and have a uniform set of kind of neighborhoods that it uses to assess heterogeneity, and also shares power across different arms of the experiment in determining treatment effect heterogeneity. But that, I just want to reiterate that none of the methods that I have worked on solve fundamental identification problems. They just help you estimate more systematically, reliably, and reproducibly. Thank you, Susan. Hopefully we have one place for one more question and one comment perhaps after that from me. Please, Frederick.
Sure. So thanks, Susan, for a wonderful talk. I think I want to point out to everyone, by the way, please have a look at Susan's website or somewhere to see the breadth of her work. It's truly amazing to see all the things that she's worked on. And I wanted to ask a question related to that, because you've worked on pretty sort of fundamental theoretical questions and also in a lot of different applications. And I was curious if that gives you a perspective of where you think sort of practice goes next. As you've kind of indicated, we do a lot of randomized experiments in clinical trials and A/B testing and so on. But do you have an idea of where the theory and the methods development will sort of have an impact next in terms of something that might not replace the randomized trial, but become standard practice in this kind of experiment design? Do you think it is towards bandits, adaptive learning? How do you think about that question?
Yeah, so I made a big bet on contextual bandits. I actually started working on them like 6 years ago, and I'd worked on them when I was at Microsoft in like 2010 and 11 a little bit too. I mean, I was exposed there, and I was like, okay, this is going to be, running experiments is so hard. In the social science, you spend so much time in a room arguing about treatment A versus treatment B that you're even going to go and run. You know, wouldn't it be awesome to replace that human time with a machine and do it more systematically? So I was so optimistic this was going to be a really big deal, and I was going to get ahead of this next big thing. I would say it's taken me like 6 years to get applications that even are credible. And you see they're not, they're small and they aren't interesting from an algorithmic perspective, really. They're made a lot of compromises. And they're not really, they're totally not fulfilling this idea that I'm going to let the data decide and it's going to be easy to run. They were much harder to run and use much more human time than a simple RCT. And so I'm now more cautious about them, but I also feel like I'm starting to learn how to mitigate the costs, like having an evaluation phase at the end really simplifies things. You know, it kind of gives you a worst case scenario, and also I've been working a lot on bandits that are less sensitive, because in this contextual context where you're learning a targeted treatment assignment policy, they just kept getting overconfident and going off in bad directions. In our simulations, we could never get them to perform. So that actually has generated more research on my part about making them perform better in small samples and without functional form assumptions and so on, working on learning rather than just regret. So I guess I way underestimated how hard it was going to be to get them to be something I would recommend to my social science friends. I still don't recommend them unless you have a lot of time and a lot of resources to manage them and evaluate them and plan them. It's just too hard for like one person to do it by themselves, or with like one graduate student. It's just, it takes too much time. It's not worth it. And it makes too much chance of failure. But I do still hope that now, I think maybe it's like another 5 years where it really gets to be something where it's like off the shelf and it's safe, and we have notebooks that help you plan, and we have intuition for everything that's going to go wrong, and we have great tools for simulation studies, so people can really plan them in a way that is time efficient for the researcher. So I think ultimately we're going to get there. It was just much harder than I thought. I work with large firms too, and frankly, very few large firms have implemented bandits live in their production systems. And when they have, it's for things like, you know, email marketing experiments, or, you know, it's like Facebook has them in their core newsfeed algorithm, but they've got a pretty big data set, you know, and they have an entire team that spent like, you know, 10 years building up the Bayesian optimization and implementing it and testing it and writing the software from scratch with tons of summer interns and, you know, hiring the best people in the world. So if you can do that, if you can throw, you know, tens of millions of dollars into the R&D and you have a big benefit, then, you know, you do it in production. But medium-sized companies often don't really find it worth it yet. And I've also know companies that have tested them and then rolled them back because they were too hard to manage and too time consuming. So that just says that like we haven't quite figured it out yet. We haven't figured out the theory, but also we haven't figured out the practice. And any method, you know, it's not just the statistics, it's just having a package in R or whatever doesn't solve your problems. You need to have, you know, 20 examples that show how you used it and the collective wisdom of what went right and what went wrong. And then you know how to do it. Then you can give it to a master student and they can go off and do it. But, you know, it's more than just the statistics to get you there, and more than just the algorithm.
Thank you, Susan. Related to that, Susan, I mean, I am trained as a social scientist, starting off in sociology, moving towards economics. And you just mentioned in your reply to Frederick that you wouldn't recommend for the social scientists perhaps to use this. But then what would be the recommendation? Is it to team up, or is it like what would be the recommendation to really take these things into practice and sort of using it in the social sciences in a way that is consistent? Now, you also mentioned that it takes a lot of resources, obviously, to deploy this or these algorithms, and hence the limitations that you are seeing. But what would be the practical recommendation that you would give to a social scientist watching your talk?
Yeah, well, so I would say, like, if you are thinking of yourself also as a methodologist, then the advice changes, because then, it's worth it to spend an extra year, and part of your publication will be about innovating in the methodology. And you may have students who are interested in the methodology. So like I get students from computer science coming to my lab instead of going to work with computer scientists, because they feel like they can figure out the algorithms, but they want to see how they're used. And the other thing is that I'm spilling out new questions all the time of a certain type, because I keep finding things that don't work. So here's another research question. Here's another research question. Didn't work this way. It didn't work that way. Well, if you go talk to the computer science professor, they're like, oh, that's all solved. What are you talking about? We have root and regret bounds. We're done. And so there's this mismatch between reality and theory which spins out a certain type of question. And my computer science students are publishing in the top AI conferences based on these questions that have sort of come out of our failures, if you like, our simulation failures. So I would say if you're a methodologically oriented social scientist, then it is worth it. There aren't many applications, and people are very interested in them, and you can be very successful. But if you're purely just trying to get the best nudge experiment out, probably you'll be faster to run a series of pilots and an A/B test than to spend all the time planning the bandit today. My goal is to get to where that's not true. But if I'm developing the tools that are supposed to make it not true, and it's still not true for me, it's probably not true for most people. And I have a whole team of students working on things. Now, if you're not doing Contextual Bandit, if you're just doing not doing personalization, if you're just trying to test multiple arms, and just, that's a much simpler problem. And I think that is easier to plan. We have a little Shiny app that's up if you want to play with it. There are other tools that are up there. So that's not as hard. What's hard is if you're trying to personalize, because you have all these functional form assumptions and you just need a lot of data, and it's expensive and it's hard, and targeting is subtle. So even finding treatments where treatment A works better for some people and treatment B works better for other people. Like I did this charitable thing where it's so contrived, like NRA versus Planned Parenthood. I tried a bunch of neutral charities, and there was no hope of finding targeted treatment assignment policies for $5,000 or $6,000. It would have been like $50,000 to run an experiment that would have found targeting among more neutral charities. I didn't have $50,000 for that experiment, so that wasn't really viable. So the other thing is that social scientists were often, if you buy people for $1 a person from a survey site or something, you're just really limited in statistical power. And that's one thing that makes things hard.
Amazing. Thank you very much for that. Really thorough sort of food for thought to think about for social scientists and computer scientists and beyond. Now, Susan, we are 15 minutes over time. I know that we can go for easily another hour discussing various topics and so on, but let's put a pin in this conversation, and perhaps we have you return in due time. Thank you very much. Please join me in thanking Susan for this great talk.
Thanks very much for having me. These are great questions.